So our task is to use the second derivative test to figure out where our function is concave up or down and any points of inflection. Before we can get to that, we'd find the first derivative. And yes, I could use the chain rule, but I think no, let's just go ahead and rewrite the function. This is x plus 2 times the square of x minus 2. Now let's use just two of these at a time with FOIL. So that gives us x squared minus 2x plus 4. We're going to multiply this all out some more. After we clean it up a little, x squared minus 4x plus 4. Continuing to rewrite that function, what we've got ends up being x cubed minus 2x squared minus 4x plus 8 once we combine our like terms. Okay, now that we have another version of the function that does not require the chain rule, we can use the power rule and call this derivative of x cubed 3x squared, the derivative of negative 2x squared, negative 4x, the derivative of negative 4x, negative 4, and the derivative of 8 is just 0. What we do with this is set this derivative equal to 0. We solve for critical numbers. Now, we've done this before today. Whether we factor by grouping or we factor by trial and error, this is what we've got. We have these critical numbers at 2/3 and at 2. We've used those before to try to find extrema, to figure out where the function is increasing or decreasing. But remember that we're looking for the second derivative test. So what we can do is use that first derivative and differentiate again. So we found the first derivative to be 3x squared minus 4x minus 4. When we differentiate again, we've got 6x minus 4. Now let's set that equal to 0. Move 4 to the other side with addition. Undo multiplication with division. We can reduce this. 4/6 is the same as 2/3. Well, that's the number that we're going to use to break up the number line. So let's break it up at 2/3. And we want to know where this function is concave up or down. So we test something on each side by plugging into the second derivative. So we plug in a negative 2/3. And let's say we plug in something bigger than 2/3. Let's plug in 2. When we do, we're plugging that into that second derivative. And that second derivative, was 6x minus 4. If we plug plug negative 2/3 in, I know it gives us a number, but what I'm really interested in is that's a negative number. Because it's a negative number, the function's concave down there. When we check out the second derivative for 2, and we plug in, well, whatever it is, it's positive. So I know this part of the graph is concave up. That's going to help us to answer the question about concavity. We'll go ahead and say that this side, that from negative infinity up to 2/3 we have concave down, and that we've got concave up from 2/3 to infinity. Oh, well, look at that. We've just changed from concave down to concave up. And this is not a vertical asymptote. So that means we will have a point of inflection. A point of inflection at x equals 2/3. Well, we need, if it's a point, we need x and y. So we're going to plug that in to the original function. We said that the original function was this before we rewrote it, and you can use either version. If we plug 2/3 in, 2/3 plus 2, 2/3 minus 2 squared. You can play with the decimal or the fraction. That's 2/3 plus 6/3 when you get an equivalent fraction. When you change 1 into 3, multiplying by 3, and 3 times 2, we've got 2/3 minus 6/3 squared. Well, that is 8/3 times the square of negative 4/3, which is 8/3 times positive 16/3. When we multiply our numerators and denominators, we've got 128 over 27. Okay, that means we do have a point of inflection where 2/3 meets 128/27, or if you prefer, you can use the decimal version. About 0.767 meets about 4.74. That's our job. It is done.